Hello, welcome back. In the study of blackbody radiation, a special interest was attached to the spectral distribution of energy. That is, how energy is distributed among different wavelengths or frequency and at which particular wavelength or frequency the most energy is emitted. In this figure, we have plotted emission power along frequency, and you can see that at a particular frequency this emission power is maximum. This is a characteristic graph of the thermal radiation emitted by a hot object. So we have already seen that blackbody radiates more when it is hotter. I think some of you have some confusion regarding the relationship of color and temperature. So let me repeat that. When a body is hotter, it's blue, and progressively it becomes red as it cools. You know the relation between energy and the frequency, E equal to h nu, where nu is the frequency. That is, higher the frequency, that corresponds to higher energy, that is higher temperature. Here in this figure, we plot radiation intensity against wavelength of a blackbody. Here you can see that higher the temperature, higher the frequency at which maximum emission occurs. That is, as we go up, we are plotting radiations with higher and higher temperatures. Here we can see that higher the temperature of the blackbody, the wavelength at which maximum emission occurs is lower. Or in other words, if the temperature of the blackbody which emits radiation is higher, the frequency at which we get maximum emission is also higher. Late in 19th century, a number of attempts were made to explain the distribution of energy among wavelengths in the blackbody spectrum using laws of classical physics. But the attempts were not very successful. Now let's see two well-known classical laws. First one is Wien's radiation law, proposed in 1896. According to Wien's law, the total energy per unit volume U nu d nu in frequency interval nu to nu plus d nu can be given by this expression, which states that U nu d nu equal to 8 pi h nu cube divided by c cube into exponential minus h nu by kt into d nu. So, experimentally, we can sample blackbody radiation by inspecting what emerges from the hole in the cavity. So, if we plot the experimental curve, it will look like this, and the plot obtained by Wien's law is shown by this dotted line, and we can see that the Wien's law matches with the experimental curve only for high frequency region. Okay. Then Rayleigh Jeans Law, proposed in 1900. Considering the radiation inside the cavity to be a series of standing electromagnetic waves, Rayleigh Jeans proposed this form for the blackbody spectrum, which states that u nu d nu equal to 8 pi nu square by c cube into kt d nu, where k is the Boltzmann constant. In this expression, we can see that when nu tending to infinity, this u nu d nu also tends to infinity. That means we will be getting a shape like this. But in actual practice, we know that u nu d nu goes to 0 as nu tending to infinity. This is called as ultraviolet catastrophe. That means this mismatch which happens at high frequency region is called as ultraviolet catastrophe. That is, according to Rayleigh Jeans law, the energy density u nu d nu tends to infinity as nu tending to infinity, whereas experimentally we are getting this plot by which u nu d nu tends to or goes to 0 as nu tending to infinity. That is, both methods based on classical theories failed. Here we plot both Wien's law and Rayleigh Jeans law matching with the experimental curve. We can see that Wien's law is matching with the experimental curve only in the high frequency region, and Rayleigh Jeans law is matching with the experimental curve only in the low frequency region. That means classical theories fails to explain this blackbody spectrum which we obtained experimentally. Okay, that's all for the time being, and we'll see tomorrow. Thank you.